You think you understand water, you drink it, you swim in it, you wash with it, it's everywhere, it's ordinary, it's simple. Just H2O, 2 hydrogen atoms, 1 oxygen atom, basic chemistry. But here's what you haven't been told. Water is not normal. Water breaks almost every rule that other substances follow. And if water behaved the way it's supposed to, the way physics says it should, you wouldn't be here. Life wouldn't exist. Earth would be a frozen wasteland or a boiling desert. The fact that water is strange, profoundly strange, is the only reason anything lives. Let me show you what I mean. Start with something simple. Ice floats. You see this every day. Ice cubes float in your drink. Icebergs float in the ocean. Obvious, natural. Except it's not natural at all. It's bizarre. Almost every substance on Earth gets denser when it freezes. Liquid turns to solid. The molecules pack closer together. The solid sinks. That's the rule. Solid aluminum sinks in liquid aluminum. Solid iron sinks in liquid iron. Solid wax sinks in liquid wax. This is normal. This is what matter does. When you cool something down, it contracts. The molecules slow down, move less, pack tighter. Denser, water does the opposite. When water freezes, it expands. Ice is less dense than liquid water, about 9% less dense. That's why it floats. And this is not a small quirk. This is a violation of basic thermal physics. Cooling makes things denser, except water. Water gets less dense when it freezes. Why? The answer is not obvious. It's not in the textbook explanation. The textbook says something vague about hydrogen bonds and crystal structure, but that's not an explanation. That's just naming the phenomenon. If you want to understand why ice floats, you have to understand what water molecules are doing. And what they're doing is strange. A water molecule is bent, not linear. The oxygen atom sits at the center with the 2 hydrogen atoms at an angle of about 104.5 degrees. This matters because oxygen is more electronegative than hydrogen. It pulls electrons toward itself. So the oxygen end of the molecule is slightly negative. The hydrogen ends are slightly positive. The molecule is polar. It has a positive side and a negative side. And polar molecules attract each other. The positive end of one molecule is attracted to the negative end of another. This attraction is called a hydrogen bond. It's not as strong as the covalent bond holding H and O together inside the molecule, but it's much stronger than the van der Waals forces that hold most molecules together. Hydrogen bonds are why water behaves strangely. In liquid water, molecules are constantly moving. They form hydrogen bonds, break them, form new ones. The average molecule is hydrogen bonded to about 3.5 other molecules at any instant. The structure is dynamic, constantly shifting. The molecules can pack fairly close together because they're not locked into fixed positions. They slide past each other, liquid. But when water freezes, the molecules stop moving so much. They lock into a crystal structure. And here's the key. The crystal structure of ice is very open, very spacious. Each water molecule, hydrogen, bonds to exactly 4 neighbors in a tetrahedral arrangement. This creates a hexagonal lattice with large empty spaces. The molecules are held at fixed distances from each other, and those distances are larger than the average distance in liquid water. So ice has more space between molecules than liquid water, less dense. It floats. Now ask yourself, why does the crystal have to be so open? Why can't ice pack tighter? Because of geometry. Because of the angles. The hydrogen bonds have specific directions. The oxygen wants to point its negative side toward hydrogens on other molecules. The hydrogens want to point toward oxygens on other molecules. And the most stable arrangement, the lowest energy configuration, is the tetrahedral structure. 4 neighbors, 109-degree angles, lots of empty space. This is not optional. This is what hydrogen bonding demands. If water tried to pack tighter when it froze, the hydrogen bonds would be strained. They'd point in the wrong directions. The energy would be higher. So ice expands and floats. Now think about what this means for Earth. Lakes freeze from the top down. In winter, the surface cools first. Ice forms on top. And because ice floats, it stays on top. The ice layer insulates the water below. The water under the ice stays liquid. Fish survive. Aquatic life continues. The lake doesn't freeze solid. But if ice sank, the situation would be catastrophic. Ice would form at the surface, sink to the bottom, and more ice would form on top. The entire lake would freeze from the bottom up. No insulation, no liquid water left. Everything dies. And in the ocean, the same thing. Ice would sink. The oceans would slowly fill with ice from the bottom. Eventually, the entire ocean would freeze solid. Earth would become a frozen planet, glacial, uninhabitable. Life depends on ice floating. And ice floats because water expands when it freezes. And water expands when it freezes because hydrogen bonds demand an open crystal structure. It's a chain of causes. Remove one link and the chain breaks. Remove hydrogen bonding and life ends. But it gets stranger. Water has a density maximum at 4 degrees Celsius. Not at freezing, not at boiling, at 4 degrees. This is bizarre. For most substances, density increases steadily as temperature decreases. Not water. Water gets denser as it cools from 25 degrees down to 4 degrees. But then, as it cools further from 4 degrees to 0 degrees, it gets less dense again. Why? Because the hydrogen bond network is starting to form the open ice structure even before freezing. As water approaches 0 degrees, clusters of molecules start arranging themselves into ice-like configurations. Small regions of tetrahedral order. These clusters have more space between molecules, so the density starts decreasing before the water fully freezes. This 4 degrees to C maximum has enormous consequences. In a lake, the densest water sinks, so as the surface cools in autumn, water cools to 4 degrees Celsius and sinks. This sets up convection. The entire lake mixes. Oxygen from the surface gets distributed throughout. Nutrients from the bottom get circulated. This is called turnover. It happens every fall and spring, and it's essential for aquatic ecosystems. If water didn't have this density maximum, turnover wouldn't happen. The lake would stratify permanently. The bottom would become anoxic, dead zones. But because of the 4 degree lice maximum, lakes mix, life thrives. Now let's talk about boiling point. Water boils at 100 degrees Celsius at sea level. You learned this in school. It seems normal, but it's not normal. It's absurdly high. Compare water to similar molecules. H2O has a molecular weight of 18. Hydrogen sulfide, H2S, has a molecular weight of 34, almost twice as heavy. H2S should boil at a higher temperature than water, right? Wrong. H2S boils at 60 degrees C. It's a gas at room temperature. Ammonia, NH3, molecular weight 17, boils at 33 degrees C. Methane, CH4, molecular weight 16, boils at 161 degrees. All of these molecules are similar in size and weight to water. All of them are gases at room temperature. Water should be a gas too, but it's not. Water is a liquid at room temperature because its boiling point is more than 150 degrees higher than it should be. Why? Hydrogen bonds. To boil water, you have to break the hydrogen bonds holding the molecules together. Each molecule in liquid water is hydrogen bonded to several neighbors. To turn liquid into gas, you have to pull the molecules apart. You have to overcome those hydrogen bonds. And hydrogen bonds are strong, much stronger than the van der Waals forces in CH4 or the dipole interactions in H2S. So water requires a lot of energy to boil, a lot of heat. The boiling point is high, and this is critical for life. If water boiled at 60 degrees C like H2S, Earth's oceans would be vapor. No liquid water, no oceans, no lakes, no rivers, no life. The fact that water is liquid at Earth's surface temperature range is a consequence of hydrogen bonding, pushing the boiling point absurdly high. Now let's talk about heat capacity. Water has an extremely high specific heat. It takes a lot of energy to raise the temperature of water. 1 calorie per gram per degree Celsius. That's the definition of a calorie. But compared to other substances, that's huge. Aluminum has a specific heat of 0.9. Iron is 0.45. Glass is 0.84. Most substances are well below 1. Water is 1, and that's per gram. Per mole, water's heat capacity is even more impressive because water molecules are light. You get a lot of molecules per gram. Why does water have such high heat capacity? Because heating water doesn't just make molecules move faster. It also breaks hydrogen bonds. When you add heat to water, some of that energy goes into increasing molecular motion. That's temperature. But a lot of the energy goes into breaking and reforming hydrogen bonds. The hydrogen bond network constantly shifts. Breaking bonds absorbs energy. Forming bonds releases energy. The net effect is that water absorbs a lot of heat without changing temperature much. This has profound consequences for Earth's climate. Oceans store enormous amounts of heat. They moderate temperature swings. Coastal areas have milder climates than inland areas because the ocean acts as a heat buffer. In summer, the ocean absorbs heat without warming much. In winter, the ocean releases heat without cooling much. The temperature stays relatively stable. If water had low heat capacity like most substances, oceans wouldn't buffer temperature. Day-night temperature swings would be extreme. Seasonal swings would be extreme. Earth's climate would be unstable, hostile to life. Your body also relies on water's high heat capacity. You're about 60% water. That water stabilizes your internal temperature. When you exercise, your muscles generate heat. But your body doesn't overheat immediately because the water absorbs the heat. Your temperature rises slowly. You have time to sweat, to cool down. If your body were made of a low heat capacity substance, you'd overheat in minutes. Now let's talk about heat of vaporization. It takes a lot of energy to turn liquid water into vapor, about 2260 joules per gram at boiling point. That's enormous. Compared to ethanol, 855 Jg, methanol, 1100 Jg, ammonia, 1370 Jg. Water is more than 50% higher than ammonia, more than double methanol. Why? Again, hydrogen bonds. To evaporate, a water molecule must escape from the liquid surface. That means breaking all its hydrogen bonds with neighboring molecules. 3 to 4 bonds. That requires energy, a lot of energy. So water has high heat of vaporization, and this is why sweating works. When you sweat, water evaporates from your skin. Evaporation requires energy. That energy comes from your body heat. Each gram of sweat that evaporates removes 2260 joules from your skin. That's massive cooling power. If water had low heat of vaporization like most substances, sweating wouldn't cool you effectively. You'd overheat. You'd die. Plants also rely on water's high heat of vaporization. They transpire. Water evaporates from leaves. This cools the plant. It also pulls water up from the roots through capillary action. The entire process depends on water's unusual properties. Now let's talk about surface tension. Water has unusually high surface tension, about 72 millinewtons per meter at room temperature. That's why water forms droplets, why you can fill a glass slightly above the rim without it overflowing, why insects can walk on water. Surface tension comes from hydrogen bonding. A molecule in the middle of liquid water is surrounded by other molecules, hydrogen bonds in all directions. But a molecule at the surface has neighbors only below and to the sides, not above. The hydrogen bonds pull the surface molecules inward. This creates tension. The surface acts like a stretched membrane. Most liquids have much lower surface tension. Ethanol is 22. Acetone is 23. Gasoline is about 20. Water's surface tension is 3 times higher, and this matters. Capillary action depends on surface tension. Water can climb up narrow tubes against gravity because surface tension pulls it upward. This is how water moves through soil, how it rises in plant roots, how it distributes in porous materials. If water had low surface tension like ethanol, capillary action would be weak. Water wouldn't move through soil effectively. Plants couldn't transport water from roots to leaves. Entire ecosystems would collapse. Your lungs also depend on surface tension. The alveoli, tiny air sacs in your lungs, are coated with a thin film of water. Surface tension tries to collapse these sacs, but your body produces surfactant, a substance that reduces surface tension, keeping the alveoli open. If water had very low surface tension, this wouldn't be necessary. If it had even higher surface tension, surfactant wouldn't be enough. The balance is critical. Now let's talk about water as a solvent. Water is called the universal solvent. It dissolves more substances than any other liquid. Salts, sugars, acids, bases, alcohols, many gases. Why? Because water is polar. The positive and negative ends of the molecule can surround and separate ions. When you dissolve salt, NaCl, in water, the water molecules surround each Na plus ion and each Cl ion. The negative oxygen ends point toward Na plus. The positive hydrogen ends point toward Cl. The ions are pulled apart and kept apart by water molecules. This is solvation. Non-polar solvents like oil or hexane can't do this. They can't separate ions. They can only dissolve non-polar substances. But water, because of its polarity and hydrogen bonding, can dissolve both polar and ionic substances. This makes water an incredibly versatile solvent, and life depends on this. Biochemistry happens in water. Cells are bags of water filled with dissolved molecules. Proteins, sugars, DNA, salts, all dissolved or suspended in water. Chemical reactions happen between dissolved molecules. Metabolism happens in aqueous solution. If water weren't such a good solvent, biochemistry wouldn't work. Life wouldn't exist. Now let's go deeper. Why does water have hydrogen bonds in the first place? Because oxygen is much more electronegative than hydrogen. Electronegativity is the tendency of an atom to attract electrons. Oxygen is one of the most electronegative elements. When oxygen bonds to hydrogen, the shared electrons spend more time near the oxygen than near the hydrogen. The oxygen becomes partially negative. The hydrogen becomes partially positive. And here's the key. Hydrogen has no inner electrons. When it loses its share of the bonding electron, it's essentially a bare proton, a very small positive charge with no electron cloud to shield it. This tiny exposed positive charge can get very close to the negative charge on another molecule's oxygen. The attraction is strong. That's the hydrogen bond. Other elements can form hydrogen bonds too, nitrogen, fluorine. But oxygen is the perfect balance. Electronegative enough to create strong polarity, but not so electronegative that it holds the electrons too tightly. Water's hydrogen bonds are strong, but not too strong, just right for liquid behavior at Earth temperatures. Now here's where quantum mechanics enters. Hydrogen bonds are not purely classical. The proton in a hydrogen bond can exist in a superposition of positions. It can tunnel between two positions. This is quantum tunneling, and it affects the structure of ice and the behavior of water. In normal ice, called ice IH, the protons are arranged in a partially disordered way. Each oxygen is covalently bonded to two hydrogens, but hydrogen bonded to two more. The protons can be on either side of the oxygen-oxygen line. This creates many possible arrangements: entropy, disorder. But at very low temperatures or high pressures, other forms of ice appear: ice to 2, ice to 3, up to ice 68. Each has a different crystal structure. Each has different proton arrangements. Some are ordered, some are disordered. The phase diagram of ice is incredibly complex, more complex than almost any other substance. Why? Because hydrogen bonds are right at the edge between classical and quantum behavior. They're strong enough to matter, weak enough to be flexible, and quantum effects like tunneling become important. There's even something called quantum ice, ice where proton positions are in a quantum superposition. The protons don't have definite locations. They exist in a spread-out quantum state. This affects the vibrational modes of the lattice. It affects thermal conductivity. It's subtle, but it's real. Water is not just strange, classically. It's strange quantum mechanically, too. Now, let's connect this to life. Life requires liquid water, not ice, not vapor, liquid. And liquid water only exists in a narrow temperature range. On Earth, that range is roughly 0 degrees C to 100 degrees C at normal pressure. That's a 100-degree window. Earth's surface temperature is mostly in the range of 50 degrees C to plus 150 degrees C. The overlap is good but not perfect. Some places are too cold, some are too hot, but crucially, much of Earth's surface is in the right range. Oceans, rivers, lakes, liquid water is abundant. If water's boiling point were 50 degrees C, the oceans would boil. If the freezing point were higher, Earth would be mostly ice. The fact that water's liquid range overlaps with Earth's temperature range is why life exists here. But this is not a coincidence in the usual sense. Earth's temperature is stable because water moderates it. High heat capacity, high heat of vaporization, the water cycle, evaporation, clouds, rain. This regulates temperature, removes excess heat, distributes heat. Water makes Earth habitable, and Earth's habitability allows liquid water to persist. It's a feedback loop. Water creates the conditions for liquid water, and life thrives in that loop. Now here's the uncomfortable question. What if water were normal? Imagine water without hydrogen bonding, just a simple molecule held together by weak van der Waals, forces like CH4. It would be a gas at all Earth temperatures. No liquid water, no oceans, no rain. Earth would be a desert, completely dry. Atmosphere might have water vapor, but no liquid. No rivers to erode mountains, no oceans to stabilize climate. Temperature swings would be wild, day to night, summer to winter. Uninhabitable. Or imagine water with slightly weaker hydrogen bonds. Maybe it boils at 50 degrees. Oceans would be smaller. Evaporation would be faster. Climate would be hotter and drier. Life would struggle. Maybe it would exist, but it would be limited, fragile. Or imagine water with stronger hydrogen bonds. Maybe it freezes at 20 degrees Celsius. Much of Earth would be ice. Oceans would freeze. Only equatorial regions would have liquid water. Life would be confined to a narrow band, limited, vulnerable. The actual properties of water, the specific strength of hydrogen bonds, the specific geometry of the molecule, all of it is finely tuned to make Earth habitable, not designed, not intentional, but tuned by the laws of physics and chemistry in such a way that complex chemistry can happen, that structures can form, that life can emerge. Water is not simple. Water is not normal. Water is profoundly strange. And that strangeness is not a curiosity. It's the foundation of everything living, every cell, every organism, every ecosystem. All of it depends on water being weird. The textbooks tell you water is H2O, 2 hydrogens, 1 oxygen. But that's not what water is. Water is a network of hydrogen bonds, a dynamic, shifting, quantum mechanical network of molecules that refuses to behave the way other molecules behave. Water expands when it freezes. Water boils at absurdly high temperature. Water absorbs enormous heat. Water has extreme surface tension. Water dissolves nearly everything. And because water is strange, you exist. Your blood is water. Your cells are water. Your brain is water with some molecules dissolved in it. Everything you are is built on the strange properties of this strange molecule. Reality is not obligated to make intuitive sense. It is only obligated to be consistent. And water is strange because the universe is consistent in a way that permits strangeness. Hydrogen bonds are strong because electronegativity differences are large. Ice floats because geometry demands open crystal structures. Life exists because water breaks the rules in exactly the right way.